Now let's come to a video where we start discussing about the quality of the energy at our hands. Now to do that, let's assume that we have a hot gas which is flowing through a pipeline. So this is the figure that you should focus on. So let me write it down. We have a hot gas which is flowing in a pipeline. Okay, so the yellow lines that you see on the screen, these yellow lines, okay, they represent a pipeline in which a hot gas is flowing and the mass of the hot gas is m. Now due to the heat loss to the surroundings due to convection or radiation, the temperature of the gas continuously decreases from inlet at state A, so this is state A, to outlet at state B. So you can say that TA is higher as compared to the temperature at state B. Okay. Now although this process is a reversible process, that is of the heat loss from state A to state B, okay, we will assume it to be a reversible isobaric path because we don't want our hot gas inside the pipeline to lose any pressure. So let's assume, let me write down this, that in actual, okay, the heat loss process from state A to state B, now this is an irreversible process. It is an irreversible process, but we are assuming it to be a reversible isobaric process between the inlet state and the outlet state, and let us assume that with the help of this figure. So this is the figure which assumes that between state A and state B you have a reversible isobaric path. So this is this line on the TS plot, it represents an isobaric path. Okay, now let us assume an infinitesimal reversible process at constant pressure. Okay, so let me write down this line. Let's assume a reversible isobaric process. And this would be an elementary process, or you can say a hypothetical small infinitesimal process. Now for this, if I have to find out the value of entropy change, that would be equal to m into Cp into dt upon T, isn't it? Because this represents the value of Q reversible, isn't it? So from here I can say that ds upon dt, or let me take it to be the other way around. Let us take dt upon ds. So dt upon ds would come out to be T upon m into Cp. So that's a nice looking expression, that is dt upon ds, which is equal to T upon mCp. Now if you may ask that why did I take dt by ds instead of ds by dt? Okay, so if you look at this diagram over here, that is the TS plot, so dt by ds, it represents the slope of the TS curve. It represents the slope of the TS curve, isn't it? So as the value of temperature increases, the slope increases, and if T decreases, the slope decreases. Okay, so let's analyze this a bit. So in this pipeline, okay, let us say that the Q amount of heat is being lost to the surroundings, okay, as the temperature of the gas reduces from T1 dash to T1 double dash, and in between these two states the average temperature of the gas is T1. Alright, so in this case the value of Q would be equal to m. Now because we are having a constant pressure process, we'll write Cp, and the temperature reduces from T1 dash to T1 double dash. Simple, isn't it? So the average temperature is T1. So I can write this down as T1 into delta S1, because this is the process which is depicted on the TS plot with this. Okay, so this is this much amount of area, which is delta S1. Okay, so the amount of heat that is being transferred is the area below the TS curve. So you can see the average value is T1. So T1 into delta S1. So this shaded red area is the amount of heat that is being lost to the surroundings when the temperature reduces from T1 dash to T1 double dash. Okay. Now if you come back to the plot, you have the temperature of surroundings as T naught T naught. Alright. Now if you talk about this, that is the temperature falling from T1 dash to T1 double dash. So this also indicates a loss in the available energy, isn't it? So the available energy lost with this heat loss at temperature T1 is, let us say, W1, which is equal to Q minus T naught delta S1. Okay, so initially you had the work output as the amount of heat input, but in this case this much amount of heat or this much amount of energy is being unutilized. So this is the unavailable energy. Okay, and the decrease in the available energy is this. So this is the decreased available energy. Now when the gas temperature reaches T2, when the gas temperature reaches T2, and we are assuming that T2 is less than T1, but obviously, because if you look at the pipeline diagram, this is the inlet and this is the exit. So the temperature decreases from inlet to exit. So this is a higher temperature as compared to this. So T2 is at a low temperature as compared to T1. Now, so as the gas reaches the temperature T2, okay, let's assume that the same heat loss Q occurs as the temperature decreases from T2 dash to T2 double dash. So this is the temperature which is dropping again, and the average value of temperature between these two states is T2, and for this temperature drop, the amount of heat that is being lost is the same as this. So these two values are same. So for the temperature drop between T2 dash to T2 double dash, I would say that Q is equal to M into Cp into T2 dash minus T2 double dash, and the average temperature being T2 into delta S2, this value. Okay, so this shaded region is again Q. Now with this drop in temperature, there is again a drop in the available energy. So the available energy lost with this heat loss at temperature T2 is, let us say, W2, which is equal to Q minus T naught delta S2. So this much amount of energy is not accounted for, and this again becomes the unavailable energy. Okay. Now if you compare, let me write down this equation and this equation again. Let me write this down. So I will have W1 is equal to Q minus T naught delta S1, and I have W2 is equal to Q minus T naught delta S2, isn't it? So let's compare this. So if you take the value for Q for this process, you will have Q is equal to T1 delta S1, and for this you will have Q is equal to T2 delta S2. So now compare these two, you can cancel these off. Okay, so you will have T1 by T2 is equal to delta S2 upon delta S1, which is a value which is more than 1, because we know T1 is higher than T2. This means that delta S1 is less than delta S2 and T1 is greater than T2. So these two things are very, very important. Now let's look at this. If you have to compare between W1 and W2, now the amount of heat loss is the same, Q. This value is a constant, T0, isn't it? This is less and delta S2 is more. So delta S1 being the lesser quantity as compared to delta S2, so this would be a larger difference as compared to this difference. So this means that W1 becomes greater than W2. Okay, so this means that the loss of available energy is more when the heat loss occurs at higher temperature as compared to when the same heat loss occurs at lower temperature. So if you look at this, that we were talking about W1, so this is the amount of available energy loss when the heat loss occurs at temperature T1, and this is the available energy loss when the heat loss occurs at temperature T2. Now when the comparison is done, when the comparison is carried out, we come to know that W1 is higher than W2. This means that W1 was the amount of available energy loss at a higher temperature and W2 is the available energy loss at a lower temperature. So this means that when you lose heat at a higher temperature, you lose more available energy as compared to losing heat at a lower temperature. So for example, if I say that a heat loss of 1 kilojoule at, let us say, 1000 degrees Celsius, okay, is more harmful than the same heat loss of again 1 kilojoule at 100 degrees Celsius. So losing heat at 1000 degrees Celsius is very harmful as compared to losing the same heat at a much less temperature. Okay, so this means adequate insulation must be provided for high temperature fluids to prevent the heat loss. So when you have the fluids of 1000 degrees Celsius flowing through your pipeline systems, then you may need to add very adequate amount of insulations. Okay, now this may not be so important for low temperature fluids since the loss of available energy is low. Okay, now same can be said that when you have very low temperature fluids, then yes, you have to again add adequate insulation so as to prevent heat gain from surroundings. Okay, so this is a concept that tells us about the quality of energy loss, that if you lose energy at a high temperature, it has more detrimental effects as compared to losing energy at a low temperature. So this affixes a quality to energy of a system. So I will write this down. This affixes a quality of energy, or you can say quality to the energy. Quality to energy of a system. Alright. So this means that the quality of energy of a gas, let us say at 1000 degrees Celsius, is much higher to that of the quality of energy at 100 degrees Celsius, because the loss is much more detrimental as compared to the loss at 100 degrees Celsius. Okay, so an awareness of this energy quality as of energy quantity is essential for the efficient use of our energy resources and for energy conservation. So the concept of available energy provides a useful measure of this energy quality. Okay, so this is a very, very important concept to understand. Okay, now after this concept of the quality of energy, let's move on to the next topic and talk about the maximum work in a reversible process.